Yeah, because it's essentially like the idea is how do you organically get to the triangles, right? And when I was doing the editing for our last video, I was we started like it's actually pretty interesting how that video flows in a way that was totally uncoordinated, but it flowed really well because we started off talking about the fidelity and the information in quantum states. And so you get to the triangles based off of the nature of quantum states and what they are and the information contained in them. So the triangles themselves are a representation of the information contained in quantum states.
Mhm.
Yeah. And so if you remember from
Where's the
last
link
week,
happening exactly? Like where's the link like intuitively, where's the link? And then how did you even come up with that idea? Like, where is it coming from? Is it
yeah. So it comes from classical probability theory.
okay?
So it just comes from the idea of information theory as understood by Claude Shannon,
Okay.
which is to say that in information theory, to gain information during a communication is measured by the amount of surprise. So if you are so in other words, if you can predict the outcome of something with 100% certainty, then you're not surprised. And the
Yes.
only reason why you could predict the outcome is because you already had full information. You already knew what was going to happen. And so to look at an observation and be surprised is to gain information. And so this idea of surprise can be captured in probability distributions. What's the probability of this happening or that happening?
Okay.
So if you have an experiment, you're asking yourself, my theory has a hypothesis. If the hypothesis is correct, then I should be able to predict the future. Like that's the idea. It's like, um, if yeah, if my theory can predict the future, then we start saying that it has value. So this is or that it has truth, and this is the basic foundation for creating truth in science. And so, with that being said, we know that probabilities are associated what's likely to happen. And so if you have a probability distribution, then you can compute the entropy associated with it. And the amount of entropy in it tells you the amount of information it has, i.e., it tells you the ability, like it tells you the capacity that you can predict the future. So again, if you have like an 80-20 coin and you're flipping the coin, then 80% of the time it's gonna flip heads. So if you had to bet your life, like if someone gave you this coin and said, "All right, guess how this is going to land, and if you get the answer correct, then you live, and if you get it wrong, then you die." And you know that the coin's the 80-20 coin, you're gonna bet heads every time.
Yeah.
Right? You're going to predict, like, if I bet heads, there's a good chance I'm going to live. And then you probably will live because the probability distribution is telling you how likely you are to be able to predict the future. But if it was a 50-50 coin and someone said, guess whether it's going to land heads or tails, then you're just like, I have no idea what's going to happen. I'm just going to pick something and I might live or I might die. I have no clue. I can't predict the future at all. So the nature of experimentation is in science is the nature of can I predict the future? And so this is associated with information, and this is what's contained inside of quantum states.
Yes.
Yeah,
Yeah. So far, so good. So far, like I think anyone can understand, even basic physics and math, they can understand what you're saying so far
yeah,
about
yeah.
this.
And so with classical probability distributions, you have like I was saying in the last video, you have like a classical random variable, which is just a set of possible outcomes and a set of probabilities associated with them. And so for something to be a probability, so if there's only 5 outcomes, then when you do the experiment, one of the outcomes has to happen, right? So that means that the probabilities associated with each possible outcome, when you add them all together, has to equal to one. So any probability is a number between 0 and 1, right? And they're all positive numbers. So it's a positive number between 0 and 1. And when you add all the possible outcomes, the probability of all the possible outcomes together, then you get one. You get a probability of one because you're saying something like, well, it has to be one of them. Does that make sense?
Yeah. Yeah. So far, so good. Yeah. Makes
Yeah.
sense.
And so this is where the triangles come from. For just a classical probability, for a classical random variable, um, yeah, for a classical random variable, these conditions that the sum of the probabilities have to equal one in that the probabilities are all positive numbers that are in between 0 and 1. This ends up creating your triangle. So the triangle emerges from the condition and the constraints of probabilities for a classical random variable.
Okay, but these random variables, you're talking about experiments that we do, right?
Yeah, they're like experiments. They're like the probability of an outcome of an experiment. So you
Yeah,
can
probably
pose
the outcome of
everything.
an experiment. So like we
Yeah,
measure it, and then we have different classical probabilities. But see, like you jumped too far that I didn't understand like where the triangles are actually coming from.
yeah. So in this regard, like for me, I need to sit down and like actually work through the proof, but there is just simply a proof. Like there's a mathematical proof
Yeah,
of this. You can
but
just
just
Google it.
intuitively, how do they arise?
Well,
Like
it's like
why triangles, not another? Like why not circles or why triangles?
yeah, so intuitively I can give you some basis. Think of it this way. For two dimensions, two possible outcomes. So for two possible outcomes, so this is oh, say this is heads, and this is tails. This would be 100% heads and tails. So you can kind of think of it in terms of a two-dimensional case.
Okay.
Essentially, this vector here represents the idea of getting heads 100% of the time, and this represents the idea of getting tails
Hey, that
100%
was
of the
100%.
time.
Yeah, yeah, yeah.
And the thing is that the length of these vectors is associated with the probability.
Yeah.
Yeah. So
So
that means, huh?
okay, I understand it when two-dimensional, like it has or tails, and then it can be anywhere between the two, right?
Yeah, what the thing is that the length of this vector has to be equal to the length of this vector because the
Yeah,
length is associated with probability.
yeah. Okay.
And so the one in the middle is associated with a 50-50 with 50-50, and every other point on this curve, on this line between them is a different probability. This is a different choice of probability. So this right here represents the space of your probability distribution with the constraint that so this vector right here. So if we want to write these down in terms of vectors, so we call this the heads basis vector, the tails basis vector, and then call this one the p vector. Okay. So we're going to call this the heads basis vector. We call this the tails basis vector, and then let's call this vector here probability vector p. Let's see.
I think the quality of your video went down a lot.
Oh,
Now it's back. Now it's good. Now it's good.
yeah. You know when that happens, sometimes it doesn't. When you actually see the actual recording, it doesn't
Oh,
manifest.
okay.
Yeah. So let me break this down. And yeah. Oh, yeah. So it's like this. Can you see that? Is it clear?
Yeah, P equals P has plus PT tails. Yeah, okay.
Yeah.
Okay, so
So
but
so
this is a two-dimensional case, and then how does
yeah,
it
so this would be like a so this line right here represents what would be like a one-dimensional simplex because essentially what you have is you have two dimensions, right? I have two dimensions in terms of the probabilities. I have heads and I have tails. These are two independent variables. But because you have the fact that the sum of the probabilities has to equal one, then you have one constraint, which means that the dimension of possible probability distribution to the one-dimensional space. So if I have an experiment with three possible outcomes, then there's one constraint which is that the sum of the probabilities has to equal one. So you get a two-dimensional object for a experiment with three possible outcomes. Then you get a probability distribution space that is two-dimensional, which is the triangle. And then if you have four possible outcomes, then you have then you have a probability distribution space that's three-dimensional. And so your space of your triangle is always one dimension less than the number of possible outcomes that you have. And so this is really just a basic fact of classical
yeah,
probability that
yeah,
comes from
I've came
yeah.
across this. So it's like yeah, it's always one less. But then so to you for the simplex to be a triangle, like in this case, then you had to have three possible outcomes.
Yes. So when I say simplex, I use the word simplex specifically because it's dimension agnostic. So you can just say like a one simplex, which it would just be a line. A two
Yeah.
simplex is a triangle. A
Hmm.
three simplex, and you can just keep going in higher dimension if you just use the word simplex as opposed
Isn't
to
like a
triangle, which is
circle same thing? Why not a circle?
why not a circle? I mean, this image right here kind of tells you why it's not a circle, right? It's
Yeah, but
like it's like
um this is in 2 dimensions.
yeah. So basically, if you do it in three dimensions, then it just kind of extends like this. Here, let me show you.
Okay. We have 3 dimensions, but it's still a triangle.
Well, now it's two-dimensional triangle.
Yeah.
Right? So in here, it's just two possible outcomes. So it's a one-dimensional simplex, which is just a line. Then when it's three possible outcomes, so outcome one, outcome two, outcome three, then you have just a triangle.
Okay.
And it's and remember, because the vertex here represents 100% probability of observing here, then the length of this vector has to equal to one, because the probability at this point right here means that the probability of land of this is zero, the probability of that is zero, and the probability of this is one. And it's the same for all of them. So the distance from the origin to to a vertex is always one. And then this line right here, this line segment here is associated with this having zero probability. So this has zero probability, but it has a probability between here and here, which brings you back to the two-dimensional case, right? So this right here represents a two-dimensional case if you say that the probability of this third option is zero,
Yeah.
and
Yeah.
then the
And
points in
then
the middle are is just any possible probability distribution
three. Yeah.
of the three. Yeah,
Hmm. Okay. So this is the idea. So basically, it's all about vectors in space that are the basis vectors, right?
yeah,
And
which represent the possible outcomes.
the possible outcomes. Okay. And the actual basis vectors are the extreme cases, if you know what I mean. If it's
Yep,
like, yeah.
yep.
And then
Extreme cases of absolute certainty.
yeah, and then the possible outcomes are made out of these possible like basis vectors, and we can have different directions. And those possibilities are contained within a triangle.
Yeah, so think of the possibility, like each point on the triangle is a probability distribution. It's saying something like the point in the very center of the triangle is one third, one third, one third. So
Yes,
the point in the center of the triangle is one third, one third, one third.
but you already like the triangle. There could be so many different triangles.
Um,
It's not just one triangle.
what do you mean by that?
I have to visualize. Like you have the base. Okay, let's say with 3 dimensions, you have like x, y, z.
Mhm.
If it's just a vector in the x direction, that means it's zero on the other ones, right? And it's just yeah, and so we have that. But then we can have any direction from the origin to any point in this in three-dimensional space, right? And that point would have like a combination of the three possibilities, right? Of x, y, z.
Any point on the triangle does, because the triangle emerges from the constraint that the sum of the probabilities has to equal one.
Oh, okay. That's why there's only one triangle in this case because of the
Yeah,
constraint.
yeah,
Not we can't have multiple. It's just that constraint. Okay, I see. So
yeah.
now we
That
have one triangle within this three-dimensional space that we
yeah.
have created because of the constraint.
Yes, because of the constraint. Yes, yes,
Okay.
yes, yes.
Okay. I
Exactly.
see that
Yep,
I
yep.
was missing in my understanding. So now, and then what's the next step after
Yeah. So what we've just done is we've set up why the triangle represents probability distributions for a classical random variable.
classical?
But
Okay.
yeah,
Hmm.
and so from the last video, I demonstrated that the information contained in quantum states, um well, so let me put it this way. Let me think. Yeah, because it's not only that you have that it's like in our last video we were talking about the idea that from a quantum state you can extract classical probabilities. But I don't think that's the relevant thing here. The relevant thing is that if you remember from last video, we had two different types of quantum states. We had pure states and mixed states,
Yes.
where a pure state is a state where if Alice and Bob are doing an experiment, then Alice prepares a single state in the same way for each trial. So she prepares one state and she sends it to Bob. And then and so the information in his wave function in his quantum state, that's telling Kim the probability of what he'll observe if he makes measurements of a particular observable. So he could be measuring position, he could be measuring momentum. And so he has his quantum state, he has his observable, He takes the eigenbases of the observable, which are all the possible outcomes. So it's like all the possible positions that he could observe. He applies each one of those to the quantum state, and that produces a probability of observing position one. Then and then another one with position two. And then if he takes the set of all possible positions and applies them, then he gets a probability distribution, and he has a classical random variable like the one we just constructed.
Yeah. So the quantum is coming from that each experiment could be different because it's all probabilities, right?
Yeah, yeah. Basically, what I'm saying is something like, what we've set up is the nature of the information inside of a quantum state. The nature of the information inside of a quantum state is that it is a thing that can produce a lot of classical random
Yeah,
variables.
yeah, yeah.
Yeah,
Because we're doing because like you said, like Alice is sending the same quantum state every time, and then Bob is the one who has to observe it, right?
yeah, yeah.
He
He's
has to
making measurements. Yeah,
So every time it's different probabilities. It's like we reset every time. It's not like classical when it's like the same exact every time, the same exact outcome. Now we have different probabilities each time, and then he's basically taking an average of all the outcomes, and that shows a classical probability distribution. Is that correct?
yeah. I think that's correct. Wait, say that one more time.
So Alice is sending. It's the exact same experiment being done, and
She's sending the
the
exact same
thing
state.
he's getting is the same, but not the same because it's quantum, right? So each time he observes it, it's like an observable, like let's say momentum, it would have different probability distributions each
Well,
experiment.
he would have different outcomes. So in other words, it's like he has momentum. He has one quantum state, and then he has the set of possible momentum outcomes. And so for each trial, she's sending the one state, and he might measure momentum one measurement, and then the next trial he might measure momentum two. But if he does like 1,000 trials, then eventually what he should get in terms of what he observes should be a distribution consistent with the information in the quantum state. So in other words, the quantum state itself can extract a classical probability distribution, and when he does his experiment, then his results of his experiment after many trials should be consistent with the probability distribution that's extracted from the
Yes.
quantum state.
Yeah, that's
Yeah,
what I was trying to say.
yeah.
So, and then when you say Alice sends the quantum state to Bob, like what does that mean exactly? Like in real life?
It just means that you have some sort of device that produces like a qubit or something. So you have some sort of physical system
Mhm.
that is designed to produce a quantum state. You could be using parametric down conversion to create entangled particles of light, like whatever it is. You're just creating. You have some physical device to create a quantum state, and when you're creating that state, you have basically imagine that each device has a bunch of knobs. So if I turn the knob this way, it produces one state. If I turn the knob that way, it produces another state. And so when I'm saying that she's sending the state exact same
It's
way,
nice.
exact same time, she's having the knobs fixed. She's like, all right, I set the knobs to this, and then I run the machine, and then it produces a state, and
Okay.
I send that to Bob.
Okay.
Yeah,
And he's observing. He's observing it after.
and then he's making measurements on it.
Right.
Yeah. And so that's a pure state. But for a mixed state, then of course, like we were talking about in the last video, you have the possibility for Alice to uh, you know, tweak the knobs. I'm gonna send him this state 30% of the time with these settings, and I'm gonna send him this state 70% of the time with these settings. And so now the quantum state associated with Bob's observations is a mixed state because she's taking the quantum states and she's mixed them with classical probabilities of sending one 30% of the time and one 70% of the time. Um, and so this is what we call, and so we represent these with what we call density operators. And this is where I want to get into where what I've done with the triangles, because essentially there always exists a reference frame in which a quantum density operator looks classical, looks like a classical object. And this is consistent with what we talked about in the last video, where we talked about the nature of superposition. Remember, depending on your basis with which you make a measurement, your quantum state might be in a superposition or not be in a superposition. Being in a superposition is not a necessary requirement for a state to be quantum. Because if I have the, if my state is oriented, if my state is oriented in the z direction and my detector is oriented in the z direction, then I'm going to measure z up every single time. And so when I say in the z direction, I mean my state is oriented in the z up direction, my detector is oriented in the z up direction, and so if that's the case, then I get z up with 100% certainty every single time. But if I were to have my detector in the z direction and then I rotated my state to be in the x direction, now it's a superposition. So superposition completely depends on your choice of basis, and it depends on your perspective. And so it's in that same way, when you have a density operator, there always exists a reference frame. There always exists a reference frame in which the object appears classical. And so in the little note that I was making you the other day that I didn't send you, I came up with this picture here. You see it?
Yeah.
So this right here represents a density operator. And what I've done is this is what I call like a diagonalization. So because of the nature of the density operator as being this object that represents probabilities, it has to maintain these constraints of if I were to extract the classical probability distribution out of this, then the probabilities that I extract from this quantum state have to be between 0 and 1, like with the classical, just like with the reasoning behind the triangle. They have to sum up to 1 and they have to be between 0 and 1.
Yeah.
And so because of that, there always exists this capacity to diagonalize the density operator. And diagonalization means that it only has values along the diagonal, and all the values on the off diagonal are 0.
Okay.
So the reason why this is important is because if you don't diagonalize your state, then those off 0 components represent superposition. So in quantum mechanics and quantum information, if you have a density operator and it has only values along the diagonal, then that is equivalent to having a classical state, like a classical probability distribution. You're back at the triangles again. But if it has values off diagonal, those off diagonal terms represent superposition.
Hmm.
And so in the theory of decoherence, you can actually see they can actually measure decoherence of a quantum state by looking at like the magnitude of its off diagonal terms. And then if the quantum state interacts with the environment too much, then it loses its off diagonal term, then it becomes a classical object. This like something like a wave function collapse happens and it
Okay.
becomes a classical object. And
Okay.
so but even before you do that, there always exists the capacity to take a density operator that is not diagonalized and then diagonalize it.
Okay.
And, and so in one of my slides that I showed last time, I can write rho like this. Okay. So what this right here represents, say, Alice's mixing process. So n is the number of pure states that Alice has. Because remember, um, the reason why the states are mixed and not pure is that she can choose to send like one pure state one time and one pure state another time. And so n tells you like the number of things she's
Yeah.
mixing together.
Mixed states are made out of pure states.
Yes, mixed states are made out of pure states. So these are the pure states that Alice could be sending, and then this is the probability with which she sends them.
Each one. Yeah. Yeah.
Yeah, and so she can do that with 15 pure states, 20. Like there's no bound on how many of these she can choose. Like
Yeah.
she
Yeah.
can do whatever she wants.
Uh-huh.
But when I diagonalize it, I reformulate the density operator in its eigenbasis. So this eigenbasis, uh, and so this is the eigenbasis, and then these are the eigenvalues which are associated with the probability. But you'll notice that the summation now is over the dimension of the dimension now. So the dimension is like the number of possible outcomes. So for a qubit, it's 2. For a qubit, it's 3. And so this dimension tells you like the number of possible outcomes that you can get from your from measuring the quantum state. And so what this now represents is when you look at the quantum state, the density operator in its eigenbasis, then you get this situation.
Okay.
where it has no off diagonal terms, which is identical to what I was saying before about the idea with superposition that I can just change what I'm the orientation and it changes whether or not there's superposition. It's the same concept.
Okay. I got it so far. So, and this can happen every time, right? Like diagonalizing the
Yes,
density
diagonal.
object every time. There's at least one case when you can do that.
Yes,
And
exactly.
so that means there's at least one case where it acts classically.
Where it appears like a classical object. Yes.
It's a quantum object acting classically. What
Yes. Yes.
exactly? Okay.
Just like the idea of the superposition. If my state and my detector are aligned, then I get the thing I get measurements with 100% certainty. But if they're not aligned, then now I get superposition, which is the quantum behavior that you expect. So
Okay.
this is this
Can
is
you explain that, like the superposition and the basis? Can you like?
Yeah. So in the last video, I explained it in the last video because it has to do with how you represent the state. So remember, the idea of quantum states, like the mechanics of quantum mechanics, is that quantum states themselves mathematically are treated as vectors in Hilbert space. So like
Yes.
they're these vectors in Hilbert space. And um and so within that Hilbert space, you have another space which are a space of operators. So I take my vector and then I can do some action on it. I can operate on the vector. I can do something to it. And some of those operators are called observables.
Yeah.
And so when we have our vector in Hilbert space, we want to extract the information in it, and that information is a probability distribution, right? And so for each observable, I can extract a probability distribution from my quantum state, from my vector in Hilbert space. And so um And so what that means is that what probability distribution I get depends on my observable, right?
Yes.
So different observables give you different probability distributions.
Okay.
Now, the thing is that if my quantum state itself, as a vector in Hilbert space, is an eigenstate of one of my observables, which is to say something like, I have my observable's position. There are three possible positions that I can measure, right? And my quantum state itself is actually the vector position 2, right? So it could be position 1, it could be position 2, it could be position 3. The quantum state itself is position 2. So what that means is that this observable or this quantum state is in an eigenbasis of one of my observables. And when that's the case, then when I make a measurement with this observable, if it's in that eigenbasis, then I get this outcome 100% of the time.
Yeah. That's
And so,
classical.
huh?
That's classical.
And yeah, and then it appears more like a classical object. Um, and the thing is that the reason why that is that if you were to take a pure state, yeah, because this goes again with the density operator. If I take a pure state like psi, then there always exists something like it's what we call like a rank. It's a rank 1 matrix, which is that to say that it has one value in one spot and then 0 everywhere else. This is not a good explanation. Something like this. So, in other words, if I have a pure state and I'm representing the pure state in its own basis, then it looks like this. But if I represent the same pure state in a different basis, then it'll have all these off diagonal terms and everything.
Yeah.
I don't know if I'm making this clear
Oh
or
yeah,
not.
yeah. That's like linear algebra. That's every like basic linear algebra.
Yeah, yeah.
Okay.
And so the point is like the thing that I want to drive home the most is this fact. This is the fact that I want to drive home the most. Any density operator can be diagonalized.
Can be diagonalized. Okay.
Any of them. And so what that means is that because that's possible, then I can always work from a perspective that I'm dealing with a classical object.
Yeah. And this is the trick, the kind of a trick that you're using in your research.
Yes, yes. This is my main trick. This is the thing that I think differentiates me from a lot of people. Um, yeah. And so what that means is that so now it's like, okay, so now if you're gonna work in this space where everything's diagonalized, it's like how do you manifest the quantum then?
Exactly. That's my question.
Yes. And so from my research in fidelity, the quantum is completely manifested by now having more than one triangle. And so this is something that you couldn't do before. So in class with a classical probability distribution, it doesn't the mathematical structure of that space doesn't have multiple triangles for a classical random variable. But with quantum mechanics, you can make more triangles due to unitary transformations. And the unitary transformations are associated with the algebraic structure. And as I've been saying before, like quantum mechanics, like the essence of quantum mechanics as captured by mathematics is all algebra. It's the algebraic structure. It's the fact that I can actually, for a two-level system, like for a classical two-level system, it's flipping a coin. It can be either be up or down. For a quantum two-level system, I have three different axes I can measure. I have a z-axis, an x-axis, and a y-axis, and the relationship between these axes are all generated by unitary transformations. That's what the quantum is. That's like the Heisenberg uncertainty principle emerges out of this. So it's the algebraic structure that captures the essence of quantum mechanics.
But can you explain a unitary transformation?
Yes, unitary transformations are information preserving transformations. They're symmetry transformations. They're reversible. They're essentially, if you want to think of them in a very intuitive way, they're just rotations. It's rotation. That's what it is. It's a rotation.
Rotations of what? Like,
It can be of anything. It can be of the quantum state. So remember, quantum states
okay,
are vectors in Hilbert space. So if I apply a unitary, I'm just rotating it. It's literally
you're
just rotating
rotating,
the
and
thing.
then what changes? Like, okay, with information is preserved, but then what changes? Other than the orientation, what does that mean when the orientation changes?
Yeah, so if the orientation changes, so remember, so in the video that I did on the uh uh observer. So I did a video on what a quantum observer is. And what I was trying to explain in that video is that the quantum state itself doesn't have any information without its relative orientation to a detector. So in other words, when I do so if I keep my detector fixed and I rotate my quantum state, then it changes the statistics of what I see.
Okay,
So in other words, it's like taking my quantum state and then rotating it, uh taking my quantum state and rotating it is effectively changing the what I observe when I make a measurement. But if I were to take my device and rotate it with my quantum state, so for every rotation I do with my quantum state, I do
then
the
as if
rotation,
nothing happened.
then nothing's happening. Yes.
Okay,
And I can keep my quantum state fixed and rotate my
okay,
detector, and that's
yeah,
equivalent to keeping my detector fixed and rotating my quantum state.
yeah. Okay,
Yeah. So that's what
um,
the unitary transformations are doing.
okay. So now that's the
And, and,
thing. I
and if you look at that video I explained to you, it's like it's all has to do with symmetry. So it's like, yeah,
now for someone like me who's not that deep into like how you are, like PhD in physics,
yeah.
you're saying that it's all algebraic transformations, and it's all basically vectors in space, and the space we're dealing with is the Hilbert space, and then we have an orientation of the quantum state, and then we change the orientation. But like in real life, physically, in an experiment or anything, what does it mean to have a different orientation of the quantum system?
I mean, I feel like I don't know. I'm trying to figure out. So I feel like I just explained it. So I'm trying to figure out how to explain it in a different way. I mean, there's a lot of things. Like one of them is like shortening the equation. For example, like you have phase. So here's an example. So for an electromagnetic wave, um, yeah. So for like a wave that's traveling, for example, Uh, yeah, this is a good example. So for a wave that's traveling to in one direction, it has something called a phase angle. And
Okay.
so if I were to take like a straight line, a fixed line, and say the wave is traveling in this direction, right? And so because it's a wave and it's traveling, then that means that um as it passes through, going this way, and then let's see. Okay. So I tried my best to draw the same wave. So if it's gonna be kind of funky. So this is at like time zero, right? And then this is like some later time. So it's traveling from this direction to this
Yeah.
direction,
Okay.
this at time zero, and this at some later time. And you can see how because it's traveling in this direction, that the intersection between this dotted line, and the wave itself, like right now it's entering at a trough, and here it's entering at a hill, right? And so that's associated with the phase difference. So this is like the distance traveled d. So the distance traveled d, so I've traveled some distance, has changed where this ends up when it crosses this line. And so when you're looking at these phases, you can look at this in terms of the unit circle. So because this wave pattern is a repeating pattern, so that means that as if this imagine that this line this wave it goes on for infinity or whatever, and so as it's traveling from left to right, it's gonna continually because it's a repeating pattern. It's gonna go from trough to bottom. It's gonna keep on passing all of those, and so that would be equivalent to just going around in a circle. So this would be 0, this would be 90 degrees, 180 degrees, 270 degrees.
Yeah, yeah,
So you can model where this wave is during its cycle using a circle where it
yeah,
says
yeah.
0
Circle. I
degree.
know, I know that. Like that, I
Yeah.
know.
So these are your phase angles. And so when you're looking at something like a unitary transformation, then you can literally think of it in terms of these phases. And so the difference in orientation is associated with a change in phase. And this is important because now when you have interactions, like when you have interferometry, the whether or not you get constructive or destructive interference depends on the relative phase between the waves that are interacting with each other. And so in this regard, this is like one of the best physical examples I can give. That would be a unitary transformation. The change in the phase is a rotation in the phase, and that actually results in different interference patterns based off of the relative phase between the waves that are interacting. And that would be like that's one example.
Yeah, yeah. Okay.
Yeah.
Yeah, that's really good. So now, okay, so now let's go back, and then we were talking about how classically there's one triangle, but with a quantum, the nature of quantum mechanics allows to have two triangles for the
Yes.
possible
Yes.
outcomes. Can you explain like how it goes from why we can have two, and
Yes. Yes.
what significance does that have?
Yes. So this goes into the heart of quantum mechanics, which is that like I was saying, is that quantum states are vectors in Hilbert space. And the Hilbert space itself is characterized by the symmetry group that's associated with it. So in other words, it's saying something like if I have a vector, then I rotate the vector. Like I have a vector and then I rotate it. And I keep the length of the vector the same. So I haven't changed its length or anything. I've just rotated it. Um, the nature of this rotation is characterized, or like the ability to do this rotation, or the matrices associated with this rotation, are characterized by the symmetry group of the symmetry group that is that characterizes the Hilbert space. And so, in other words, what I'm saying is that you have a Hilbert space. It has a symmetry group. That symmetry group has representations. These representations are unitary transformations, and these unitary transformations are represented by matrices. So you have some sort of matrix that takes a vector, an input of it takes a matrix that takes a vector as an input, and then it maps an output vector. And if it's a unitary transformation, it doesn't change the length of the vector or anything; it just rotates it.
Just
It
rotate.
just does a
Okay,
rotation.
got it. But then, how do we know what symmetry group is associated with what Hilbert space? What decides that?
Uh, I'm trying to think. I think this goes into a little bit beyond my ability to explain, but if you look at things like spin, for example, there's this whole Dirac equation and stuff like that. Like there's association with relativistic quantum mechanics, and like you end up, and I think the Dirac equation is a thing that ends up giving you spin. And so, uh, I think that it's a consequence of like measurements and experiments and just going through and looking at what must be. I don't have to think about the history of it.
Okay,
I'd have to think about the history. I'd have to think about that question
but
a
then
little deeper.
why symmetry groups? Like why symmetry? Why is symmetry important in this?
Well, the Schrodinger equation itself is like the Schrodinger equation itself is derived by unitarity. So it's derived by making unitarity with hold. And so the best way I would explain it is something like when we are evolving quantum states and we're rotating them with respect to some Hamiltonian, like there's some Hamiltonian that dictates the evolution. Like when you solve Schrodinger's equation, you have to give it a Hamiltonian, and then solving that gives you like the unitary transformations associated with that Hamiltonian. And so the reason why it has to be symmetry like this is because it has to do with the quantum state not interacting with the environment. It has to do with the fact that non-unitary transformations are associated with collapse, wave function collapse. They're
Mm-hmm.
associated with decoherence. They're associated with interactions. And so, if the system is isolated and it's just evolving according to Schrodinger's equation, then it's going to be unitary. But it's symmetry and unitary because it has to preserve information. Non-unitary transformations don't preserve information, which is associated with a collapse and decoherence and interaction. That's why.
Okay, that's just the nature of it. Basically, was what I'm getting.
Yeah, I mean, the quantum mechanics has to reflect the nature of the physical system. And so what I'm saying is that if you have an interaction where the information is not preserved and it starts bleeding into the environment due to decoherence, then that's a non-unitary transformation. That's a non-information preserving transformation.
Okay.
Yeah. And so yeah, so that's why it's like these symmetry transformations, because the idea is that the evolution that is dictated by Schrodinger's equation um is one that is associated with a system evolving in isolation and not interacting with the environment in a way that changes the nature of the state. And so it's all about preserving information and preserving relationships. And that's like the derivation. That's how you derive the Schrodinger equation.
Mm-hmm. Mm-hmm.
Yeah.
Okay, so okay, let's go back to like why the two triangles
Why the two
in
triangles,
Hilbert
yeah.
space. Yeah.
So going back to the idea of rotating the vector,
Yeah.
of rotating vectors. So like I was saying, if I have a three-dimensional Hilbert space, then that means that there exist three pure states that are orthogonal with respect to each other. So if I start off with one pure state, then I can generate two orthogonal pure states, right?
Yeah.
Anyway, and so what the way that I was thinking was, it's like, okay, well, because I know that, then I can start off with my pure states and I can represent these pure states by a vector, by these vectors. So this is three dimensions. So I can represent each one of my pure states by these vectors: 1 0 0 0 1 0 and 0 0 1, because they are orthogonal to each other in three dimensions. And then I can take my unitary transformation. I can take a unitary transformation and I can apply it to this vector. So this is just the rotation. This is this
Right.
rotation being done. So
Yeah.
it's like, okay, I can take this unitary and I can apply it to this vector. And I can take that same unitary and I can apply it to each one of those vectors. Because remember, the unitary itself represents the symmetry group of the Hilbert space. And the symmetry group of the Hilbert space means that you can rotate between all equivalent vectors. So these vectors are equivalent because, again, whether or not it looks like it's rotated completely depends on the basis. If I change my basis if I change the basis when I change the vector, then nothing's happening. That's
Yeah.
the nature of it. Like that's the core nature of all of this. It's something like symmetry comes from equivalence, because the thought of a change is merely due to the existence of an observer. It's due to an
Yeah.
existence of a basis.
Okay. I understand that.
So what this means is that if I take the same unitary and apply it to each one of these, then these things are going to remain orthogonal to each other because they're all being rotated by the same
The
amount.
same way. Yeah. Yeah. Okay.
Yeah, they're all being rotated by the same way, which then creates my triangles. So it's because of the fact that Hilbert spaces themselves have this algebraic structure associated with them.
Unitary transformations that preserve information.
Yes.
Okay.
Yes.
And
Yeah.
this is the space that quantum states live in.
Yeah. Exactly.
So we have okay, that's what you're saying. We're saying we have one triangle. We do a unitary transformation in the Hilbert space, and then we have another triangle, but we have the same information in both.
Yes. Yes. Yes.
And so they're essentially the same, just oriented differently in the same space.
Yes. Exactly.
Okay. Now we have to get into how that is important and like what is that? How is that? And then how is it different classically? Classically, the way it's different is that these unitary transformations don't exist in a classical. What's it called?
Probability
Vector.
for
Yeah,
a
yeah,
classical random variable.
yeah. So that we can now do unitary transformation
Correct.
classically. That's
Yes.
why we're only left with one triangle. So now in Hilbert space we have two. Okay, so
But
what's
we
so
have we have we have a continuum. We have a whole
continue? Yeah,
continuum.
yeah. You can do so many transformations. Okay,
Yeah.
and
Yeah.
it's infinite unitary transformations can happen, right?
Yes. Yes. Yes.
So then how does that help us? What's so important about that?
Okay. So what this does is it helps us visualize the space. So I always choose the symmetry group SO3 because that's associated with Euclidean three space, which is the space we live in. We live in three, like we our everyday experience is a three-dimensional Euclidean space, and so the SO3 represents rotations in that space, and so I can visualize it. So I was just like, okay, well, I want to visualize quantum fidelity. I want to visualize these things that are going on. So if I just make everything diagonal, then I can visualize these triangles, and then I can
Uh,
just rotate the triangles.
and that's why you're diagonalizing in the first place. So it's easier
Yes,
to visualize.
yes, yeah. It's that reason, and because the object looks classical in that perspective. So there always exists one perspective, in which the quantum state appears as a classical probability distribution. Yeah,
Okay. And it's
and so
easier to visualize also, like, so that's two reasons for that.
yes, and so because it's a classical, because it appears like a classical object, I can interpret the triangle using classical intuition, which is to say that I'm interpreting the quantum state of the triangle. And I wish I had a graphic. I mean, when I actually upload the video, I'll have a graphic to point to. Um, uh, yeah. So when I actually look at the triangle, remember each one of the basis vectors represents a possible outcome. And then the points on the triangle just represent the probability of observing one outcome versus another, which is just a basic like a random variable, like a basic experiment. So what this means is that I gain an intuition for what this triangle represents, of what this quantum state actually represents. But the weird thing is that if I rotate one triangle, I keep one triangle fixed and I rotate the other one, then that means that these outcomes of this experiment are different from the outcomes of this experiment. They
Why is it?
represent they represent two different
Oh,
experiments.
because okay, with different orientation, that means different outcomes. Okay.
Yeah. Now they're
Uh,
different outcomes. But something you said earlier, which is mind blowing, is that you said, well, because these are unitary transformations and they have to contain the same information, it's all just
yeah.
a matter of orientation or perspective.
Mhm.
And so what it's saying is something like, one, if I want to do quantum fidelity, I want to compare two quantum states. If the quantum states appear on the same, uh, they appear on the same probability simplex, then that means that what you're asking the question is, if I have a coin, right? And one coin has a distribution of 80-20, and the other one has a distribution of 70-30, but it's the same coin, then you're asking how similar is the information in these distributions. So you're just comparing two different probability distributions. You're saying something like, uh, I have the same physical system, the same experiment. I just want to know that if I were to change the weighting of the coins, how similar are the outcomes? And that is something that's just like it's like you literally can just compute an overlap like this. So you can think of this as being like the two different probability
Yeah, like it's
distributions
just a
on the same
classic.
experiment.
Classically, we can understand it classically
Yeah,
completely.
yeah. You can see that, okay, they're pretty similar right there. And then if they look like this, then it's like, oh, these things these things don't even have the same possible outcomes, right? Like I know for a fact that the set of outcomes associated with this have nothing to do with the set of outcomes associated with this. These are orthogonal. These are orthogonal to each other, and then we know if they sit directly on top of each other, then we know that they're exactly the same. And so this is like the inner product for a classical probability distribution. You just want to know how similar is a
Yeah.
probability distribution. Yeah. Um, but when you're trying to compare two quantum states that exist on different simplices, this has to represent one experiment, and this has to represent another experiment. But it's not that these experiments are totally unrelated; they're related by the unitary transformation.
Okay.
So they're
Same,
not.
same information, different experiments.
What's that?
We're getting the same information, different experiments.
Well, this is the kicker, because it's like the uh the the difference appears when you compare them next to each other. Like it's something like they are different experiments when you're comparing one with the other. So this is confusing, but basically what I was saying is that if I have two points that exist on two different probability simplices, and I'm trying to ask what is the similarity in information between these two things, Before, if they both exist on the same thing, it's just a matter of looking at the distribution and how much overlap they have. But with this, because one exists over here and one exists over here, then this experiment, this point is associated with the outcomes of this experiment, and this point is associated with the outcomes of this experiment. So now there has to be a question of how similar are the two outcomes? What's the relationship between the outcomes of this experiment and the outcomes of this experiment? Um, and and once you have that difference and trying to compare two different what look like classical objects with different experiments, that's where all the quantum happens. All of the crazy quantum crap emerges from that fact alone. So it's something like you can see something like the quantum mechanics emerges when I start asking the question, when I start trying to compare quantum states that exist that are related by two different experiments, but the outcomes of those experiments have some sort of relationship between them.
Hmm.
Does that make any sense?
I have to come up with some questions. So one triangle, we do a unitary transformation, we get another triangle. Those two are related. And then what's the relationship between the two triangles, like in physically in real life? What are they, like, what's the relationship between them? Other than, okay, geometrically, they're just unitary transformations of one another.
Let's see. Wait, ask that question again.
So like geometrically, they're unitary transformations of one another, the triangles.
Yeah.
But in real life, like
Yeah.
how are they related?
So one way I like to think about it is like imagine that one triangle represents like a dice, you know? So there's like two ways I can deform the dice. I can take the dice and I can change the weighting inside of it, which changes its probability distribution. That's like taking one simplex and choosing a different point on the surface. But then imagine I take the dice and I can start there's like some continuum of transforming its properties. So it's like as I rotate the object, you can imagine that say the material that the dice is made of is continuously transforming as I rotate the object, or say that or say I'm deforming the length of it or something like that. It's like from one, I'm starting off with a piece of plastic that's like a six-sided dice, and then as I rotate on some other direction, it becomes like an eraser with like a six-sided eraser that's like elongated or something like that. You're
Okay.
like actually changing the physical. So in one experiment, you're asking what's the probability of observing one of the six sides of this dice, and then the other, if I roll the dice, and then the other experiment is asking something like, well, what's the probability of this eraser, this rubber eraser, what side it will land on if I roll that. And you can imagine that the unitary transformation describes the relationship between the dice and the eraser. So you're like deforming you have a different experiment.
Yeah. Okay. And those two are related to each other. They're unitary transformations of each other.
Yeah,
The
yeah.
Hilbert space, they look the exact same. It's just one is oriented in a different way.
Yes. So this is the confusing part because it's saying something like if I have only one triangle, if I don't have a fixed triangle and I only have one triangle, then that means that when I rotate this, so that means that I only have one basis with which I can observe this thing. So before the basis I chose is 100, 010, and 001. And if I rotate the triangle, but there is no relative comparison, then the basis stays the same. In other words, depending on which triangle's perspective I'm using, like whether I'm looking at it. So basically, it's like when I have these two triangles, I can look at this triangle from this triangle's perspective. If I'm looking at this triangle from this triangle's perspective, i.e., I'm using the basis of this triangle to look at this one, then this one has off diagonal terms and looks like a quantum object. But if I'm using this basis to look at this triangle, then this one looks like a classical object, and this one looks like a quantum object.
Yeah, yeah, yeah.
So depending on which triangle's basis you're using to look at different triangles, it changes the basis from being this 100 thing to actually taking on the columns or the rows of the unitary itself. And so I'm saying all of this because essentially if you have one triangle in isolation, then there's no capacity to look at it from a different basis. You're always looking at it from the 1 0 0 0 0 0 1 0 0 0 1 basis, which means that you can't observe any difference at all. So this whole idea of transforming from a dice to a rubber to a rubber uh, um, eraser, that's gone. It has to be just one experiment. So that means that when I rotate the triangle on its own with no fixed reference, then I'm not doing anything. It's a pure symmetry transformation. You can't actually tell anything. It's only when I keep one fixed and I rotate one with respect to the other that I suddenly get physics. And this goes back to the idea of what I was talking about earlier with this. It comes back to this example here. Because essentially what's happening is that when you have two waves and they interfere with each other, what you get depends on their relative phase. So like what's their relationship? Like is this one trough to trough? Is it, if you look here, well, these, yeah, yeah. If you look here at this point, then you have like a difference in phase. Like it's a difference in phase, and so physics emerges when you have a relative relationship between two waves and they're able to interact. But if they're isolated from each other, and I rotate and I allow one wave to like move to the right, I let it move from left to right. If I'm an observer and I'm also moving left to right as the wave is moving left to right, nothing is happening, right? And so the idea that when the wave moves left and right, something physical is happening, it all depends on the observer. Nothing is in isolation, nothing is happening. It's all an algebraic transformation. You can't actually tell anything is happening, and that's the nature of a symmetry transformation. Symmetry transformations, the nature of them is that when the transformation is done, you can't tell anything's happening. And so and so and so because otherwise it wouldn't be a symmetry transformation. And so what you're saying is something like this rotation we know does absolutely nothing, but then if I fix one thing and then I do the rotation, now it's a completely different experiment, and now physics is happening, and now you have this. It's bananas. But the kicker of the thing that's really good about all of it is that at the end of the day, I just have two triangles, and
Mhm.
so as a visualization, just looking at it as a visual object, I have two classical random variables, two classical objects. Even though when I look at this object from this one's perspective, it looks like it doesn't behave classically, but that's all just a matter of perspective.
Okay. So essentially, all the quantum stuff is coming from perspective.
Yes.
Okay. And you did this whole thing so you can just make it easier to grasp and like make your point come across in a good way where anyone can visualize, and it just makes everything just easier to understand.
Well,
That,
it wasn't. I wasn't even thinking of people when I was doing this. This was during like this was. I was knee deep in the pandemic at this point, working from home on this stuff. And I was trying to understand quantum fidelity. Like quantum fidelity is so confusing. It's weird, and essentially, it's something like quantum fidelity, when you look at it, how it's defined, like how it's derived, is we call it the Ullmann-Joseph fidelity. That's like the standard quantum fidelity that we use, the Ullmann-Joseph fidelity. And this fidelity was derived from quantum mechanics by looking at classical fidelity and trying to go, okay, what are the characteristics of classical fidelity? And then how do we generalize those to quantum? And so the development of fidelity itself was a far more of a mathematical desire for consistency from going from one to the other. And so when you look at its physical motivations, it's really confusing. I mean, it has like five or six different ways to interpret it. Like you can interpret it in terms of uh like I show the equation, but you can interpret it by looking at this thing called the geometric mean operator, which has to do with doing parallel transport across fibers in a fiber bundle. Like, and all of that crap is only needed when I have two things that don't have the same eigenbases. So in other words, it's something like the definitions of the quantum fidelity that I was getting in textbooks. I could not comprehend how they corresponded to what you measure in a lab.
okay.
Because one of them was like it's like it's like, and this is why I get into the purifications. One of them is something like I have one quantum state that exists on this triangle, a quantum state that exists on this triangle. Then I take them and I purify them. I construct their purifications, and then from these pure states, I look at the orientation between the I look at two pure states on these two different manifolds, and I look at the maximum overlap, and then that's the fidelity. You're like, what the hell is that? What does that mean? Like, why the hell would I go to purification space and look at the overlap between purifications to tell me about how similar information is that I measure in a laboratory? Like, I don't understand that at all. And so it really came from a desire to be able to see quantum fidelity with the hopes that I can gain some intuition about what the hell it
Mm-hmm.
means.
Mm-hmm. Okay.
Yeah. And for me, the desire to visualize was really important. And so by constructing things in this way, it gave me something that I could look at. And
Mm-hmm.
then I just reasoned through the idea of like, okay, well, if I have the Hilbert space, then it has a symmetry group that characterizes it. The representation of that symmetry group are the unitary transformations. Those unitary transformations can take a single vector, a quantum state in Hilbert space, and rotate it to all other vectors in Hilbert space. So that means I can access the entire space. I can access the entire space simply by using the unitary associated with the Hilbert space. Then I know for a fact that every density operator is diagonalizable. So what I'll do is I will take this standard basis, this orthogonal basis, 100, whatever. Like you can always start off with that, no matter what Hilbert space is starting off with. You just start off with 100, 01, just do that for whatever how the dimension is. That creates an orthogonal basis, and then because the unitary transformation gives me access to all of the quantum states in the Hilbert space, then I know for a fact that I can get access to all of the probability diagonalized density operators by doing these unitary transformations. So I know I have access to the entire space of density operators, and I know that I'm treating them all as these classical objects. And so it's like this is a perfect setting for me to just like start looking at stuff based off of triangles and rotations.
Okay. That makes a lot of sense now.
Yeah.
Thank you. Okay. I think you explained it really well. But can you like explain again? I know you did, but can you explain again, like why is this significant, and why aren't other physicists looking into this?
I mean, I don't know. Everyone has their own approach on how they do stuff. I think one of the reasons why is because I'm so a lot of times it's very easy to work on things that are specific as opposed to trying to generalize everything. So some scientists like to work in a far more generalized space. And because I was so focused on visualizing things in SO3 and Euclidean 3 space, um, that was just a difference in preference and interest in just doing it that way. To be honest, I don't really know why more people don't do it this way. Like it seems very intuitive and clear to me. I mean, maybe someone will see this video and see a glaring flaw in what I've done somehow, but I don't think so. But they might. But I think it's very simple and convenient. Um, and so I needed that simplicity to function in this space. So it's just the thing that came out of a need, I think. The reason why it's significant, I really do think, is because this ability to look at these two different quantum states as classical objects. Because now you can use classical language to describe what's going on quantum mechanically. So like in what we just did is I talked about this idea of two different experiments. Like we know for a fact that these quantum states, the information contained in them, is telling you something like the probability of making a measurement. Um, and so we know for any experiment, and with that setting, that an experiment is consists of a set of possible outcomes and a likelihood of observing those things, which is something anyone can understand. And then we know that if I have one basis over here and one basis over here, then these have to be related to two different experiments because I have the eigenbasis over here, the eigenbasis over here. These are two different experiments. But still, this is still just an experiment with three possible outcomes and a probability distribution associated with it. So no one's lost. Like this is very, very comprehensible, I would say. And then you start understanding that the another benefit to me is it really highlights this insanity of symmetry transformations and where physics, like the nature of physics. Like to me, it's absolutely bananas that if I have one probability simplex and I have nothing to compare it to, then when I do a rotation, it's equivalent to nothing happening. But then suddenly, if I keep one fixed and look at the other and look at one oriented with respect to it, then suddenly I get this idea of two different experiments. Whereas before we know, so in other words, these experiments have to be equivalent and not equivalent. They have to be the same and not the same. They're the same experiment, but they're not the same experiment. They has to be. It's absurd. Um, but it's the nature of perspective. And to me, this captures the nature of perspective that is contained implicitly inside of quantum mechanics. And what I'm demonstrating with this whole triangles same and not the same is the same thing I was communicating with the idea in my video on the observer and how the information in quantum states actually is a relative thing. And there's actually a field of like an offshoot called relative what's it I don't know. It's not. I don't think it's called a relativistic quantum mechanics, but it's like relative quantum mechanics, where people have made these arguments. So I'm not the only one making these arguments about the nature of quantum, about the nature of information in quantum states is actually relative. It's just obvious. Like anyone who does quantum mechanics knows that superposition, superposition, no superposition. Like it's just how it works. Um. So yeah. So to me, the benefit is something like a clear language to communicate. Um the nature of quantum, but also it tells you the rupture between classical and quantum. Everything, if they share the same eigenbasis, everything's classical. If they don't share the same eigenbasis, now suddenly you need the full mechanics, you need the full structure of quantum mechanics, the full mathematics of it to describe like something like the fidelity or how similar two quantum states are. And the mathematics that arises from it is the same mathematics of gauge theory. You end up having these fiber bundles, and you're looking at parallel transport in the fiber up here, while you're having a trajectory in the base space. And so you actually get into very rigorous mathematics, and there's a lot of overlap between this space of purifications and things like quantum error correction, quantum entanglement, because you can explain quantum entanglement in terms of this. So now like, you have a clear setting and space to start explaining to people what quantum entanglement is, and and how it's associated with these purifications. I don't know. To me, it's just a very intuitive space to
Mm,
work in.
I see. I see. I see now. So this is what you're trying to do with your research. Is start from this space and try to explain more stuff in quantum mechanics through this idea.
Yeah. I would say it's more like I've stumbled on this space to do research in. And from this, I have come across like a lot of low-hanging fruit, like a lot of really interesting questions. Like questions can be posed in this space with relative ease. Like, for example, here's an example of something that can be posed from this. So I had this image. Let me see if I can just pull it up for you. Where's the best place? This is one of my favorite images because I think it's really helpful. Here it is. Share this. You see it? So what's interesting about this is that you have a wider view of the space, and then you have a side view with one dimension suppressed. And what you notice is that it's like all the quantum states. So like I was saying before, pure states are states with maximum length, and maximally mixed states are states with the smallest length. So any point in between this circle and this circle, or this sphere and this sphere, is a valid quantum state, right? But the thing is that if I choose a point here, for example, you can see that I can rotate my blue simplex to intersect that point. And so the meaning of that point, like the physical meaning of this point, comes from the actual simplex that intersects that point. So that means that, like I was saying, each simplex represents an experiment. So that means that the point itself gains its meaning based off the simplex that is intersecting it.
Okay.
But the thing is that you can see here that you can have two simplices intersect each other. So in the bottom version, you see a whole line of points that intersect each other. And so when these two different probability simplex intersect each other, what you get is that these points have two different meanings simultaneously. Like it has meaning associated that's given to it from the experiment of the blue triangle, and then the meaning associated given to it from the experiment of the orange triangle.
Yeah.
So I remember for a while back, I was working on that problem. Yeah. Oh, yeah. I forgot. Yeah, I forgot about that one. Oh, yeah. So one thing I forgot was that, yeah. So there's several things that I've done. One of the calculations that I did is I was actually able to visualize the quantum fidelity process, like actually able to visualize it as a trajectory on a curve of these manifolds. So um, I was able to do that. I was able to isometrically embed the surfaces of ignorance into three-dimensional space so to actually visualize the literal geometry of ignorance. So I'm actually able to literally take these fibers in this fiber bundle and then visualize them as like geometric objects. So I'm actually able to visualize the geometric objects like as something that you could put in like a 3D printer and hold in your hand. So it's like the objective geometry of like quantum ignorance,
Mhm.
and like of these fibers. But I also was able to actually look at what I think are like quantum entanglement in terms of I don't know if I have these images. Let me see if I can find them. Anyway, maybe it's something that we can go on to later. But essentially, what I have is I have like 5 or 6 different results that I could actively publish on right now if only I had the time and funding for someone to allow me to do it. And a lot of this stuff touches on very foundational and fundamental aspects of quantum and quantum information.
Mhm.
And you don't need much more than triangles and like rotations to like
Yeah.
understand what's going on.
Yeah. That's why this is so interesting. Like,
Yeah.
yeah, I know now. I see the vision that you have.
Yeah.
I see why like you're so passionate and excited about getting all this information out.
Yeah, because it's like, you know, and maybe next time I can start getting into some of the research results that I've gotten. Maybe I can start maybe I can go into the details of the idea of entanglement and the arrow of time. We might be able to go into that. Or I could just pull out some of the results that I've gotten from this space already. And there's like there's like ways to analyze yeah, there's a lot. I mean, yeah, there's a lot here, man. Yeah.
I think what we did today was really good. Like you explained from the bottom up what these triangles mean and why they're important.
Yeah. Yeah. That was the goal. And then, of course, when I actually post it, I'm gonna add in visuals so people don't have to just look at my hand gestures and can
Yeah,
actually, like, see it something an object
yeah,
to but, yeah, I mean, it's weird, and I think that this nature of the same but not the same, like, it doesn't make sense. Like, it's kind of absurd, actually.
yeah, yeah. That's why quantum mechanics is so interesting.
Yeah. 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 But anyway, man, I appreciate you doing this with me.
Yeah, it's my
Yeah, I
pleasure.
think
I have a lot of fun talking to you.
yeah.
Very
I
interesting.
Anyway, so I guess we can go ahead and stop recording. But